Hi everyone, my name is Asif, and today I'm going to talk to you about the current status of our project Genome ICs, which is using novel hardware and software solutions for efficient genome analysis. This project is funded by the European Union and the Saxon government through the Validierungsförderung initiative. Before talking about the solution, I'm going to start with the problem itself that we're trying to solve in this project. So, if you look at the revolution in sequencing technologies, so when the first human genome was sequenced around 2 decades ago, it costed around 100 million US dollars, and it took 10 years to complete. But today, we can do the same thing in less than $100, and it takes a few hours, in the worst case, a few tens of hours. Now, in theory, this has the potential to enable many amazing applications, including personalized and precision medicine, including early disease diagnostics. So, for instance, in preborn kids, and so prenatal diseases, and then also kind of improving the biodiversity and so on. But we haven't seen those applications yet. And part of the reason is the huge mismatch in the amount of data that these sequencing technologies are producing and the potential or capacity of conventional computing technologies, right? So these sequencing technologies, they produce raw data. And for these applications to be enabled, so this data must be analyzed to kind of extract some useful insight out of it. And with conventional computing technologies, with the huge mismatch, the huge gap between the potential of the two, it's very difficult, if not impossible. Now, in the recent past, we have seen some technologies which we can call unconventional technologies, and they have been used in other domains like machine learning very effectively. And that's exactly what we're trying to do in this project, to use those unconventional computing technologies for genome analysis. And what this needs basically, or what this requires, is to kind of develop the software stack around it to enable seamless execution or seamless running of conventional genome analysis pipelines on this in this emerging hardware. So genomic basically stands on three pillars. So the first, as I mentioned on the previous slide, is to use unconventional hardware or unconventional computing systems. So what exactly does that mean? I will give an example on the next slide. Then we want to develop this software stack that kind of talks to or integrates the existing analysis pipelines and then enables their effective execution on the underlying hardware, exploiting the properties of the exploiting the properties and full potential of the underlying hardware itself. And this also requires then kind of algorithmic transformations to kind of co-design for these novel architectures. Okay, so in theory, as a result, so we expect to reduce the execution time and energy consumption by around 10x. And in terms of like the monetary benefits of it, so this is a proxy also for reducing the overall analysis cost by more or less the same factor, because the way we are doing the analysis today is that we upload the data. So in most cases, we are doing the analysis in the cloud, and the cost of the analysis is proportional to the amount of the time it takes for the analysis to complete in the cloud. So if you reduce the execution time itself, it reduces the analysis cost by more or less the same factor. Okay. Uh, in here, I'm just showing one part of the analysis pipeline, which is computationally also the most expensive one. So it's called base calling. And again, in here, I'm just giving one example of one part of the analysis pipeline, but in here, I'm showing that this one, for instance, is using the machine learning model. So in this case, it is using a transformer model and then also a gated MLP. In both cases, this is just a profiling of state-of-the-art base caller model from the Oxford Nanopore. And the amount of time they take is basically 50%, 50% each. So the point I'm trying to make here is that the way we're doing it is that we take basically the analysis pipeline, and then from the analysis pipeline we profile it to find out what is the part in the pipeline that is consuming most time, so the most expensive part. And then we take that most expensive part, in this case the base calling, and then we again profile it to find out, okay, what part of the base caller model are computationally the most expensive one. And this here is just one example. Okay, when I say unconventional hardware, what I mean by that is that in here I have, if you look at the top part of this figure, so this is showing the conventional computing systems that we are having today. So it's the von Neumann paradigm, the von Neumann system. So we have the CPU on one end, and then we have the memory unit on the other end, and they're connected through data bus. Every time the CPU wants to do some computation, it asks, requests the memory for the data. The memory sends the data to the CPU. CPU does whatever it wants to do on the data, whatever computation is needed, and then it stores the results back in the memory. Uh, but if you look here, I mean, even if we improve the performance of the CPU and the memory by 100x, the eventually it does not guarantee reduction in the execution time by 100x because we are bottlenecked by the channel or bus in between, right? So if we cannot, even if this can process data 100x faster, but if the bus cannot deliver the data 100x faster, it will be idle most of the time, right? So this is something that is called the von Neumann bottleneck in the computing architecture community. And because of this, so this has been actually quantified that the data movement alone for data intensive application can take more than 60% of the total system energy consumption of the total system energy. And because of that, people have started moving now computation closer to the data. It's called near memory computing or in memory computing. And the idea is that now you don't, I mean, if the data resides here, it makes more sense to do the computations also here on this side. It does not make sense to move the data every time to the CPU and then storing the results back. Instead, now the CPU is working as a control unit. So it just issues instructions, says, do this computation, and then the computation takes place closer to the data and the results are stored back. Okay, so then for the software infrastructure, so this again, now if you have like a totally new paradigm, then here it's a radically different system. This also means that you cannot use the existing software stacks or the existing, let's say, compiler tools to to run your application on these novel hardware, right? So we are using this kind of hardware, and to use it, we also needed to develop a compilation stack. So we developed our own compiler infrastructure, which starts from the application representation that it's basically the same. It's hardware agnostic. So that means you don't need to change your input application. And along the line in here, this is basically we're doing some like a kind of a hierarchical lowering. And along the way, we are doing analysis at each step, and then also optimization specific to the hardware as backend. So in here we can have the existing conventional computing technologies, but the focus in here is on these unconventional hardware technologies. So I mean, we call it backend, and the backend can be an existing computing system, but in our case, we are also using at least two unconventional computing systems as well. When I say algorithmic transformation, what I mean by that is that what we're trying to do is to see if we have an input application. So for instance, in here, let's say is a computational graph of the application where each node, let's say, represents some operation and the edges, let's say, represent some data and data flow. By algorithmic transformation, what I mean is that can we transform this application to something else? Let's say that something else is on the right side. And in here, you can see that this already, if each node is some computation, in here we have a lot fewer computations compared to this one. Of course, in here, since we're doing genome analysis, accuracy is a prime factor. And that's something we are taking into account as I'll be explaining in the next slide. Okay, so where we stand today. So we started with a system called UpMem. UpMem is a near memory computing system. And what UpMem does is that it basically puts a simple RISC processor on a memory bank. So it is doing truly like closer to data computation. And that's what we started with for the base color model. If you look at the execution results here, so in here I mean, every bar represents one hardware technology. So we have the conventional FPGA, the FPGA PL, then we have the UpMem system, then we have the FPGA AIEs. This is specific for AI applications. Then we have the version 2 of these AIEs, and then we have the GPU in here as a state-of-the-art, very powerful GPU. If we look at the results, so we see clearly that the GPU in here, so higher is better, is throughput. So the GPU still is having the giving us very good throughput for different precisions and different data types. It's compared to UpMem, it's greater than 10x. Then for this is again, this is not radically, or this is not truly unconventional, but this is also something which is also not conventional. So for this, we also this is super difficult to work with actually. So we had quite a few sessions with MD and others to to be able to run something on this architecture. But if we look at then again at I mean, at the throughput per watt, or at the, let's say, the ops per watt, which is basically also a metric that captures the energy consumption. And here we are seeing that the again, in here, higher is better. So we are seeing that this AIEs, particularly the version 2, they are providing better results. For the UpMem, in here we used it, and the conclusion in here is that UpMem is basically not very good at doing matrix multiplication. So that's why it is. So I mean, we do not expect to have very good results, particularly for the ML-based base caller models, which is the state of the art. So that's why we moved to these AIEs, and particularly AIEs version 2. And as I said, in here we definitely see some improvement. In it's not 10x, but again, this is only one part. It is not combined with the algorithmic transformation that I will be explaining next. At the application level, so in here is only the base caller. And I mean, in here is only one part of the base caller. If we run the entire base caller, the GPU is still taking the least amount of time in terms of execution time, again, not capturing the energy in here. And what we're trying to do right now is basically to port what we had here to the entire base calling, and that eventually, hopefully, once it is complete, so we will have results similar to this graph in here for the entire base calling model. Okay, for the algorithmic transformation, so this is again the transformer network. What we did here was to basically prune layers of the transformer. So similar to the graph that I showed previously, where we were pruning some specific computations. So for instance, here, so we were pruning the specific synapses, or I defined it as computations. So we started from a kind of a dense graph and ended up on a sparse graph. By what we did on the way was to prune some computations. What we are trying to do here is that, or what we did here actually is that we pruned some layers. And if actually we pruned them quite aggressively. So we skipped 6 out of 18 layers, which is 1/3 of the total layer, which reduces the execution time of the transformer network or transformer model by around 33%, and the impact on accuracy is less than 2%. Now, this is something that I mean, for any other application, particularly ML, for instance, this won't matter, right? So 1 or 2% accuracy loss is not a huge thing. But in here, we're talking about genome analysis, where the accuracy loss of 1.5%, that makes a huge difference. So this is why we're still trying to are working towards improving it to kind of bring this 2% accuracy loss to 0.5%, or at least less than 1%, and then see how much is the gain in performance and energy consumption when we combine it with the novel architecture solutions. As a next step, so as a first step, what we want to do is now to complete these two things and then kind of combine them and then see if the effect in here, how much is it? So again, hopefully in here we will be, if not 10x, we will be closer to 10x. But as a next step, what we want to do is to have the entire pipeline running on these technologies, and then again, the focus in here is that we cannot compromise the accuracy, or at least it has to be it. I mean, there should be no loss, or at least it has to be in an acceptable range. And again, focusing on both performance and energy consumption, reducing them. We are also, as a next step, exploring more heterogeneous systems to further improve performance. And we actually are currently part of two clusters or consortiums, German-wide. One is a special priority program of the DFG, and another one is a TRR, a Transregio project, again funded by DFG, involving 2 or 3 different partner universities. And the idea in here is to use more radical technologies, more radical systems to do computations in memory, directly in memory, not near memory. So UpMem is still near memory. And here the plan is to do in-memory computing and then see the trade-offs again in here, right? So with these technologies, they have the potential to improve performance by a few orders of magnitude. But again, in some cases, the computations are in the analog domain, and there is some loss in accuracy, and that's exactly what we'll be trying to explore, and then kind of balance the trade-offs in there. As a use case, so we hope to run the analysis pipeline, the third generation sequencing for third generation sequencing technologies from the Dresden Genome Center. And so initially we want to focus on one specific pipeline from them, and then eventually we'll also move to other pipelines. With this, I want to thank you for listening to this presentation. And again, I want to acknowledge the generous funding by the European Union and the Saxon government to fund this project. Thank you.